Hey there, welcome back. Today we're going to do 155 min stack. This is a medium. Let's dig in. So design a stack that supports push, pop, top, and retrieving the minimum element in constant time. Implement the min stack class. So the min stack initializes a stack object. Great. Push pushes the element value onto the stack. Pop removes the element off the top of the stack. Top gets the top element of the stack. Perfect. So that's like peak, I guess. And then get min retrieves the minimum element in the stack. You must implement a solution with O of 1 constant time complexity for each function. Okay, so a lot of these functions are naturally constant time. When you have a stack and you push, constant. When you pop, constant. When you just peak at the top, constant. Now get min is potentially the one that's not constant, right? So get min is potentially the one that may take longer. So let me go to the iPad here and let's just visualize a stack, right? So a stack, right? And we have an example here. So the example here puts a -2 on the stack, right? And the stack, you could imagine if this was a stack of trays, the -2 is on the stack, the 0 is on the stack, the -3 is on the stack, right? So this would be push, 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 right? Push, push, push. And pop would be, you can go ahead and you can take that top one, pop it off the stack, right? And you could see how this is constant time, right? And, you know, we can, in code, use a list to do this, right? We can append, and append will be constant, right? Another append, constant. Another append, constant. And popping, also constant, right? Pop, pop, pop. Now, the hard part about this is, let's go back here, is that we need to track the minimum. So as the minimum comes in, we need to track what it is, and possibly if a new minimum comes in, we need to overwrite it in some way, right? So let's imagine the stack is empty, right? And you have this argument, a -2, and you put it in here. Is that the minimum? It is the minimum, right? So minimum is -2. You have a 0, put it on there. Is that the minimum? Well, -2 is smaller than 0, so you don't put it on. You have a -3. Is that the minimum? It is the minimum. It's smaller than -2, and we put in this -3. Now, here's the tough part. What happens when we pop? When we pop off this -3, right, then it's no longer the minimum, right? It's already gone. It's no longer the minimum, but we've gotten rid of that -2, right? In this world, we've gotten rid of that -2. Now, can we think of a data structure we can use where we don't need to get rid of the -2? Well, I think it's staring us in the face, where what if we just use another stack, right? So I'm going to use colors here, where at this part of the stack, this is a -2 is the minimum, right? At this part of the stack, a -3 here is the minimum, right? So imagine we had another stack where that represents exactly what we have, right? Where in this stack, when we see a new minimum, right, that -2 and then the -3, we push onto this stack. And when we pop off this -3, well, we can quite easily pop off this -3, right? We still have at the top of this stack that minimum. So let's think through how this would work. Okay, we have some functions here that we're supposed to implement. And if we're just starting off, we can just implement the basics of it, right? We can implement this without the min stack. So what is a stack, right? It's exactly what we had here, where -2, 0, -3. Stack is a list. It's going to be represented as a list. When we push onto it, we're going to push onto the stack, right? Self.stack, .push that value. Pop would be returning self.stack. pop top. What is the top? Self.stack. You know, at that index, we can use a helper -1 here. That would be the top. And min. So this is what we have not implemented yet, right? So how do we implement the min functionality? Well, as we said before, whenever we see a min, so let's go ahead and delete this. Let's say we see a -2. Well, is -2 smaller than our existing min? Well, we don't have a min, let's say, to start. So yes. So let's say when we push, and let's first create the min stack, right? Let's say if there's nothing in there, right, the min stack length is equal to 0, then let's go ahead and add it. We're going to go ahead and append this value. Right, so there we go. Put a -2 there. What happens when we see a 0? When we push and we see a 0, well, then we can go ahead and check, right? So if this 0, is the 0 smaller, or possibly, I guess it could be equal to, the last element of this min stack, right? The top element of this min stack, then great. Go ahead and append that. Right? So, is 0 smaller than -2? No, right? That is false. So we will not do it. What happens when we get to -3? Is -3 smaller than -2? Well, that's true, right? So because that's true, we're going to put that, right? Got a little 2 block here, we got a little -2 here. So how do we treat pop, right? So pop, if -3 is being popped off, right, and it equals this minimum that we have here, well, then we have to pop the minimum as well, right? So if the self min stack -1 is equal to this value, right, that -3, then we also have to pop that off as well. Let's go ahead and close this so you can see all the code. Right, so what is get min? Well, get min is just the top of the stack. Perfect. Now that probably can throw an error there, because if you do get min on an empty stack, what do you expect to get? Hopefully they don't call it. But we can check for it as well. So let's test that our code. Okay, so I used push instead of append because it said push there, and we are appending actually. Appending is the Python method on list for appending to that. Okay, did we print anywhere? We did not print anywhere. So let's see what happens when we submit. So we have this output. Oh, interesting. We have a 6 here. Interesting. Oh, sorry. What is the output? So we have these two numbers. Yeah, it's really hard to tell which one's larger, huh? So this one's larger than that. And this one's smaller than this. And then this is the smallest. Okay, so let's take this input, copy it into our test case. And if we run this, we should be able to see that there was a mistake here. Okay, so what are we doing exactly everything that we wanted to do? Okay, so we're creating a stack, and we're creating a min stack. And when we push onto the stack, we look at the stack and we append the value. So that's correct. We have to do that no matter what. Now if the length of the min stack is 0, then we're going to take that min stack and append the value. Oh, I see what's going on. So I'm doing two operations, right? So length of the min stack is 0. Then I'm doing this. And then I check it, right? And I see. I could push that element on there twice. So those two if statements are not exclusive. They can overlap. In fact, they're guaranteed to overlap, right? So if I push a -2 on there, well, then the value is going to be that last element that I pushed, right? So that was a bug. All right. Good thing we have these test cases. Awesome. Well, thanks a lot for visiting. Hopefully drawing these helped in visualizing the stack and the interactions between them. So in a quick review, we have push, right? We have a function push, and push pushes it onto this, and it affects both, right? It affects this stack, and it potentially affects that stack, right? Pop does the same thing. Pop affects this stack, and it potentially affects this stack, right? Top is quite easy. Top is taking the last element, but the insight from top helps us, understand the get min is the same thing. We're taking the top element of the other stack, right? So, whereas this is the new smallest. When we pop this, then this -2 becomes the new smallest. All right. Thanks so much. If you have any questions, put them below, and we'll meet you at the next one.